In this video, we're going to very briefly go through materials, gravity, and loads, how they work on buildings and structures, and then quickly go through the different kinds of structural types or structural systems in buildings and other structures. So let's start with this, materials. In ancient times, what was most early buildings made of? Well, I guess the real answer is probably whatever was nearby, right? You couldn't order up a shipment of marble to be brought from Italy on a huge cargo ship across the ocean. You couldn't order up, tons and tons of rocks or concrete or other materials to be brought, across the country or across the city in a huge truck. Obviously, that requires the truck. It requires the infrastructure of the roads and freeways to bring it. And so the real answer is whatever's local. And there was some amazing transportation of very heavy objects like Egyptian obelisks or the rocks, the stones that were used at Stonehenge. But for the most part, when we're talking about more rudimentary everyday architecture, it was whatever was close by, and if there was stone or a quarry nearby, you would use it. If you had the right kind of soil or dirt, you could use it to make bricks, like mud bricks. So that we call that adobe. In other parts of the world, they're called mud bricks. Then, of course, a little bit later, if we had the right kinds of clays, you could use them to make clay tiles, also baked bricks, which require a kiln and a lot of heat to turn them into something that's stronger and more waterproof. We had other materials like, straw, trees, wood, branches, reeds, all kinds of plant-based material. I forgot to write bricks here. So with that, we're talking about baked bricks in a kiln. And so stone and adobe and bricks, masonry, those things are going to last a long, long time. Natural materials like these don't last hundreds and hundreds of years or millennia. So most of the buildings that we think of like as great buildings from the Egyptians or the Romans, those were all made out of very permanent materials like stone or brick. Modern materials that we use today, concrete is one of them. Glass, think about big skyscrapers made of glass, steel, and we also use wood today quite a bit, especially in Southern California. And there's some interesting things happening with wood for larger structures, and that's called CLT, or cross-laminated timber. And so some of the things that we didn't have available before are concrete that we can use in a way that combines with rebar, which is made out of steel, to make very tall buildings or big bridges, glass in large sizes and capacities, and steel. All these things are things that didn't exist in ancient times. And of course, we still use bricks, stone. When we talk about what a building is made of, we have to decide, are we talking about what is the structural materials? What's holding up the walls and the roof and the floors inside of it? Or are we talking about the non-structural materials like, it's stucco on the outside or it has wood siding? And most of the time when architects are saying, hey, what's a building made out of? We're talking about the structural materials. And then when we talk about non-structural materials, we might call them finish materials. We talked a little bit about local versus imported before. It's always important to be thinking in those terms when we're talking about materials. How do you build walls with these materials we've been talking about? Well, you can take stones and stack them on top of each other, find some glue to hold them together, and you can make walls. And then all of a sudden, we need to make some kind of a roof to give us protection and keep the rain out. It's really hard to take a bunch of stones and try to glue them together in a horizontal fashion, because the strength of the glue isn't enough to make these stones not fall down. So what you'll see in ancient times pretty often is walls that are made of masonry and then horizontal elements made out of wood, because a tree grows straight up. We cut that tree down and we can turn that log sideways, make it into a horizontal element, and it can span pretty far. We talked a little bit about masonry, and the definition of it is when you have individual units, or small things, right? So here's a stone, here's a stone, here's a stone, here's a stone. All these individual pieces, they get stacked up and they can form walls. And in addition to just plain old walls, they can form things like arches and vaults and domes. The idea of the glue or the cement, you can see this gray stuff that's happening in between the bricks here, right? That's a mortar that has cement in it. And you can also see some mortar here, and that's used as a glue to hold the bricks or the concrete blocks together. In the case of mud bricks or adobe, they're using more mud in between to glue the mud bricks together. Here's a photo from a book called Rocketecture, and it has these homes in Southern California that are made from river rock. And we have a lot of these rounded stones all along the foothills in Southern California. The rocks are washing down from the mountains and they're becoming more rounded as they come down. And in some cities in the foothills, you can barely put a shovel in the ground without finding a ton of these rocks. So they were local, readily available, and you can use them as masonry, glue them together. Going back into history, 4,000 years, this is the ziggurat at Ur, and it's in modern-day Iraq. And you can see here that the sun-dried mud bricks are actually glued together, not with more mud, but with a tar kind of substance that we call bitumen. As you may know, there's a lot of oil in Iraq, and sometimes that oil bubbles up to the surface. And if you've ever gotten tar on your foot at the beach, a very similar situation. It can be used as a glue or a mortar to hold the bricks together. Question mark, is this masonry? This is an igloo, and this igloo is made up of individual units of ice blocks. When you build an igloo, as you place each ice block, you rub it back and forth against the one below it, and for a moment, the heat created melts the ice, and then it's so cold that the ice freezes and becomes like a glue. So the answer is yes, this is masonry. Okay, I guess the question here is, what is going to happen to these two folks? Well, what's going to happen, this guy looks like he's really flopping pretty hard, like, oh, I'm falling, that's a foul, give me the call, ref. But what I'm getting at is this guy's going to fall and hit the ground, and she's going to fall and hit the ground also. So it's just a simple way of reminding us that gravity is a real thing. So when we talk about gravity and how loads work, there's two basic different types. There's tension, which is pulling. So you can see this rope here is being pulled by these two people in that direction, and then these two people are pulling the rope in that direction. And another way to think of it is when you're swinging on a swing, you can see this chain is being stretched tight here because there's weight being exerted by the person on the swing, and there's tension forces in this chain, and the chain is strong enough to resist the weight or force of the person on the swing. So those are tension. On this side, we'll talk about compression. This is a car that's been crushed in one of those junkyard giant crushers. And when we look at this stack of stones here, you see there's this tiny stone, and it is putting its weight onto that stone, and that one is putting the combined weight of those two onto this stone, and then all the way down, right? The combined weight of everything that's up above is being pushed onto the stone below it. And so when the weight or force of an object pushes down, eventually that load path, or all that weight, has to come to the earth. So when you look at this photo, here's a little kid standing, and let's say he weighs 40 pounds. His 40 pounds is coming down and splitting evenly between his 2 feet. And let's say each foot is getting an equal share of 20 pounds. And then that load is getting put into this little step stool and getting broken into more load paths that take the weight of the 40-pound person, and I guess plus the weight of the stool itself, and direct it down into the ground. So we could say there's 10 pounds here. Maybe it'd be 11 pounds because of the weight of the stool itself. But the idea is that everything is going to work its way down, in this case being distributed horizontally across the surface of the step stool and then down into the ground. We see it here with the Eiffel Tower. See it coming down and splitting into 2 different sides. It's actually 4, right? Because it's a 3-dimensional object. It has 4 separate legs. You can see that this horizontal floor here is also taking the load of it and distributing it horizontally, or in this case diagonally, through the arch and then down into the ground. So this is one of my favorite images. This is in a city in Italy, and you can see that the color of this natural stone rocks on either side very similar to the stones that were used in the creation of the building. You can see the idea of natural local materials. Hey, we want to build something? Well, what do we got? Well, we got all kinds of these huge rock formations and mountains, so let's start cutting them into stones and we'll use them. So if you look closely, you can see this texture here, and it's basically just stone stacked on top of stone, on top of stone, on top of stone. The next thing to look at is when you want to make a doorway or a window, something's going to have to carry the weight of all these stones here and take the weight of all those stones and distribute them horizontally to either side of the window. Otherwise, all of these stones would fall into the opening of the window. So when we look at older buildings, ancient buildings, what we see more often is windows or doors that are more vertically oriented. You could imagine a more modern building might have a big, wide, horizontal window. But think about what's happening with a big, wide, horizontal window. You've got all this weight of all these stones up here, and we don't have a good way to transfer those weights sideways so they can come down into the ground. We'd need something like a really strong concrete beam or a steel beam to exist here as a header above the window and take the weight of all of these stones and distribute them down and across and into the ground. So fundamentally, when you see modern buildings, we use modern materials to be able to distribute those loads to let us have large glass windows or wide horizontal windows versus older buildings that will have more narrow and taller vertical windows and doors. There's 5 basic structural categories. Post and lintel, which I don't think most people use those terms anymore, but it's essentially the same as column and beam, right? So a post is a column and a lintel is a fancy word for a beam. The second structural type is corbel and cantilever, and those kind of work together in the same way. The third is arch, vault, and dome. And those are different from each other, but they all work in the same way, and we can combine them into one structural type. Trusses and space frames, and then tensile, which sounds a lot like tension. So here's another illustration of a masonry or stacked stone. In this case, it's a little wall, and you can see that header there. That has to be strong enough to be able to take the weight of all these stones and distribute it horizontally so it can go into the ground. And you can see the same thing happening here. In this case, these are both stone lintels, and there's limitations on how strong a single piece of stone can be when it's used horizontally. So this beam here is called a lintel, and these elements here are called posts or columns. One's vertical and one's horizontal. Stone and concrete are really strong in compression. Like you could stack stones on top of stones on top of stones on top of stones, and they don't crush. Right? It's like the one at the bottom isn't going to just immediately crush and turn into dust. However, stone and concrete are weak in tension. So what's happening when a beam is spanning horizontally and it gets loaded with either its own weight or with, a floor or people standing on top of it or roofing material, it tends to bend like this. And what happens when it bends is this top side here gets a little bit shorter, gets crushed in compression, and this bottom side here gets stretched or elongated in tension. And so stone is not so good in tension. So what would happen to Stonehenge if this stone lintel was thinner or was weaker is that eventually it would develop a crack here, and like this test for a concrete beam, it would eventually break down the middle. Moving on to the second structural type, corbel and cantilever. You can see this is an ancient kind of a doorway. And so instead of stacking the stones in a vertical pattern, you can see that this second stone here gets pushed out a little bit. And then the next stone gets pushed out a little bit further, and this one here is pushed out a little further, pushed out a little further. So the idea of a corbel is when each piece steps out or staggers out. And so if you look at this, you could say, well, okay, that was the original idea if they were rectangular stones. And so each piece is overhanging or pushing out above the one below it. And then in this case, they actually shaved or shaped the stones to have this smooth kind of curve shape. This is a corbelled dome, so it's basically doing that idea, but three-dimensionally in a circle. So it's a round-shaped room, kind of like a cone, and each stone is offset slightly inward and corbelled. So you can see that this one goes like that, and the next one goes like that, and like that, and like that, and then they came and shaped each one in a smooth round shape. And so a cantilever is a similar idea. That's why corbel and cantilever are part of the same system. You can see this part of the roof here is not being supported. Right, so here's a traditional post or column. Here's another post or column, and then this part of the roof here serves like a beam to span from vertical support to vertical support. But when you look at the edge of it, from this portion going forward, there's no column out here on the edge, right? So this entire piece is being unsupported or is flying forward. So realistically, what's happening is that the beam in here is allowed to stick out on this end. And here's another example of a building that takes the idea of cantilever to the extreme. And what's happening here in reality is there's a lot of structure happening inside that solid part of the building, and it's kind of hidden in a way that doesn't look too prominent. And the result is that you get this entire area here, and the entire section of the building that has no columns or no supports underneath of it. So it looks like it's flying or floating or emerging out of the ground. The Middle Ages get a bad rap, but this looks like the single most fun way I can imagine to poop. So you can see they have these little cantilevered little pods that stick out. I guess there's a hole in there, and you go inside and do your business, and maybe you're trying to poop on the people that are down here that are trying to attack you in your castle, or maybe it's just a good way to dispose of your sewage. If we look at this part here, though, right, you see these stones, each one sticking out a little bit more, forming a corbel. And the reality is those stones are embedding deeper into the structure of the building, which isn't quite shown right on this image. Okay, so an arch is some kind of a curving system that spans and supports the weight of a roof or wall or floor above. We could probably, stand up here on this arch, and it's going to take our weight plus the weight of the actual stones themselves, transfer them that way. If we had someone standing up here in the middle, take their weight, spread it equally in both directions, that weight's going to transfer through the curving shape of the arch down into the ground. There's going to be some foundations underneath here that take the weight of the arch and the wall or people or roof or whatever might be on top of here, and push it all the way down into the earth. Another thing to notice about arches is they typically have pieces that are kind of angling, right? Sometimes it's to a perfect center point right in the middle, like in the case of arches from Rome. They use a perfect semicircle shape. This is an aqueduct that was built by the Romans about 2,000 years ago, still standing in Segovia in Spain. And the water flows in a channel that runs across the top up here. You can see that the weight of this area is being brought downward into the arch, but the arch is transferring it to either side and then bringing it down into the column, and in this case going straight down into the ground. Meanwhile, the weight of this area here, same thing, being distributed through the arch to either side and then all the way down to the ground. In a much more horizontal shape, but very similar thing. All this weight up here is being taken and brought horizontally into the ground. If you take this idea of an arch, we could take that arch and then, we could put one here, then we could put another one on this side, another one on this side, another one on this side, keep adding them along, and eventually we get this long repeated arch, and that creates what we call a vault. If you were to take one vault that's going in this direction, curving like that, and intersect it with another vault that's going in this direction, then you get that kind of really interesting plus shape here, where this looks like four pieces coming together in a square or a plus shape. And then if you were to take this arch, or the idea of a curving arch like this, and then revolve it or spin it around in circles, you can imagine the cross section through this dome is an arch, but it's been rotated three-dimensionally or spun around in circles to make a hemisphere or a dome shape. This is a church in England. You can see the underside of the intersecting groin vaults. This is a dome from Turkey. You can see it's basically a hemisphere or a half circle shape on the inside. You can see that exterior profile there, and here's a cross-section of the drawing of the main dome. Just to review, post and lintel, corbel, and arch. Those are the three most common systems. A more modern system is called a truss, and instead of just taking one piece of wood and laying it all the way across to make a roof, we can use smaller pieces of wood to span bigger spaces, bigger distances. It's hard to find a huge tree, chop the whole tree down, and use that single tree as a really long piece. In this case, we can use small pieces, put them together, and still span large spaces. One thing you'll notice about a truss is they form triangular shapes. Here's some diagrams. These are more typically a steel truss that would be used for like a bridge. The one thing that you notice here is that there's triangles everywhere, right? Like in this case, big triangle. In this case, small triangles. In this case, triangles, triangles, triangles. Triangles here that are different sizes. Similar sizes over here. Smaller ones here. Equilateral sized triangles there. And if we take a truss and we run it in the X direction, for example, and then we crisscross it with a truss that's going in the Y direction, we end up with trusses kind of going in all directions. And in this case, they're angled, so you can see that they're not vertical. They're running at this angle. But you can see there's a string of trusses going through in this direction. And then the same thing happening in this direction up to there, I think, right? And so that forms a truss going that way, and then three-dimensionally going this way, there's more triangulated elements. And so when you have trusses going in both directions, it's called a space frame. So you're actually able to span very large roofs with very thin steel members. And the last type of structural system is tensile, which use tension. And so we're carrying loads through cables or rods or things that are being pulled. So think back to that tug of war. So the entire weight of the decking is being supported by these vertical cables here. Right? So this piece of the decking is being supported by those two cables, and on all the way down. If we look at a more complicated project, this is the Munich Olympics by Frei Otto, 1972. You can see there are these curving canopies over the seats in the stadium. And if you look at this aerial photo here, you'll see there's a big post there, and then there's some cables that are reaching out and stretching to hold up the points in the center. And you'll see that there's a tension or cable, there's a cable, there's one, there's some there. This is the post that's working as like a column, and then from it these cables are hanging down and holding up parts of the roof. Last example is a similar bridge, but this one's a little more stylish. Has the post actually here at an angle, and then these cables are working in tension to support the deck of the bridge that's spanning over the river. This project's by Santiago Calatrava.